you. Thanks a lot, Bjorn, and thanks everyone for accommodating my technological issues. So I want to continue the subject I was talking about yesterday, but the talk will in some sense be independent. I just want to recall what the big picture was. And so the goal of what I'm trying to talk about in these lectures is sort of some new tools for understanding the geometry of p-adic formal schemes. And so this is essentially the version of algebraic geometry where all objects that show up are p-adically completed. And the way we were going to do this is by sort of creating a whole bunch of stacks associated to it. And these stacks, or rather their quasi-coherent sheaf theory, captures some interesting Hodge theoretic information about X. And so yesterday's lecture was all about what was happening in the top left vertex over here. I didn't actually describe what the rest of the objects were. Today we'll talk about X prism, which is kind of the main player in this business. It's going to be a stack. It comes equipped with a lift of the Frobenius. It comes equipped with a certain divisor called X Hodge Tate. It has a compactification called the symptomification. This we will not be talking about. And then because there's a Frobenius lift on X, you can just form some perfection in a stupid way by taking the inverse limit along the Frobenius. And then if you pull back the divisor, you get something over here. And that is, in fact, the thing I discussed yesterday. And so in some sense, yesterday's talk was sort of a part of the story, but we don't need to know anything about it. Today, I want to mostly focus on what these stacks are and what they can do for you. And I will try to explain two applications, or two series of applications, one in the Rham cohomology of characteristic P varieties, and one in to Galois representations. Okay, so this construction of taking X and producing X prism out of it is called prismatization. The construction, so the history here is roughly that in my joint work with Morrow and Schulze, prismatic cohomology was invented, which was defined through some side theoretic machinery. And then Jacob Lurie and I realized that one can reformulate that in terms of stacks to come up with X prism. And then we kind of got sidetracked and mostly focused on trying to understand this perfectoidization. And in the meantime, Drinfeld rediscovered what X prism was. And he also constructed this compactification, which is extremely useful for more refined applications. And people are still trying to sort of say what the optimal statements are over here, which is part of the reason I'm not focusing too much on it in this talk. OK, so that's the history. Let's get down to business. I just want to give you the key definitions and spend some time unraveling them. So definition. In this definition, R is going to be one of my test objects. So it's a P nilpotent ring. So a ring where some power of P is 0. And D is going to be a Witt vector over R. So it's given by a bunch of elements in R. And so the countable product of copies of R as a set is what W of R is. And then it has some funny addition and multiplication that make it into a ring. And so the first definition is a condition on this element. So it's a condition that we essentially saw yesterday in the definition of a perfectoid ring. I just want to isolate it. So I'll say D is distinguished if it satisfies two conditions. And they're simple conditions. So the first element, D0, has to be nilpotent. And the second element, D1, should be a unit. And so if you remember in the definition of a perfectoid ring, we were working essentially with elements of this form, except the analog of the first condition was some completeness. But nilpotence and completeness, they're not too far from each other. So it's more convenient to work with this notion. And so what are some examples to keep in mind? So I'll just mention two. One is the Witt vector P itself turns out to be distinguished. And another example is, if you are familiar with the Witt vectors, you know there's this operation called the Verschiebung, which just shifts sequences by 1. And so if you did the Verschiebung of 1, it would be the sequence which is 0, 1, 0, 0, 0, 0, 0. And so that would satisfy this condition. And so these are both distinguished elements. Sorry, maybe I should have, oops. Let me give the collection of all distinguished elements a name first. So I'm going to write W dist for the subfunctor of distinguished elements. It's a subfunctor because this condition is compatible with the changing R, the conditions that show up for being distinguished. And it's actually not a very bad subfunctor. So we're seriously going to be thinking of W as some geometric object. So it's a functor on commutative rings, but it's actually a representable functor. It's represented by a countable polynomial ring in the variables that sort of correspond to these coordinates. And this subfunctor is defined by very simple conditions. One of those coordinates is you complete along the first coordinate, and you invert the second coordinate. And that's the subfunctor W dist that we're talking about. And so these two elements, P and V of 1, are distinguished elements. And so they live in W dist of R for any R. And if you go into the theory, you will learn that this element somehow, each of these elements essentially corresponds to a cohomology theory. And so the element P ends up corresponding to de Rham or crystalline cohomology. And the element V of 1 ends up corresponding to Hodge state cohomology. And then there are sort of fancier deformed versions of these elements that correspond to other theories. Okay, right. So these are distinguished elements. And so what we want to do, of course, if you don't want to work with elements on the nose, that you're going to, well, I'm going to definitely make mistakes if I do that. You want to work with them up to multiplication by units. And so we give that concept a name. So definition, oops. Spuff ZP prism. So X prism, when X is the final object, spuff ZP is the quotient stack W dist mod W star. I guess the small thing to check here is that this condition of being distinguished is stable under multiplication by units, but it's not too hard. As I said, or as I wrote earlier, all my geometric objects are sheaves in the flat topology on p-nilpotent rings. And so when I form a quotient like this, that's the category in which the quotient is taking place. And so whenever you have a quotient stack, it's fruitful to ask, does it have some intrinsic modular description that doesn't require thinking about the numerator and then modding out by something? And so in this case, you can just say what it is concretely. And so let me tell you the answer. So for what are the R-valued points of the stack? They correspond to two pieces of data. So spuff ZP prism of R corresponds to a datum like this, where this I is an invertible module over W of R. Alpha is a linear map, W of R linear map. And then the main condition is that locally I is principal because it's invertible, and locally it should correspond to the ideal generated by distinguished element. I mean, this is not super hard from the definition. If you're familiar with the functorial points of A1 mod GM, this is a variant of the same calculation. And so this is a spuff ZP prism of R, and all these X prisms are going to live over this. If you look in the literature, this is also sometimes called the Cartier-Witt stack. Jacob and I called maps like this Cartier-Witt divisors because they're essentially Cartier divisors, but on the Witt vectors rather than on R itself, with the relaxation that the map alpha need not be injective. Okay, so that's what spuff ZP prism is. And then once you have that, you can talk about X prism for any X. And so let me just give the definition and then tell you what it looks like. So more generally, for p-adic X, p-adic formal X, X prism of R is going to be given by two pieces of data. One is you first give a point of ZP prism of R. So just the data as above. So a Cartier-Witt divisor. And then now you need this Cartier-Witt divisor to interact with X somehow. And the way it interacts is you're required to have a map from spec or spuff of W of R mod I into X. Okay, and so one word here is since this map alpha need not be injective, this quotient here is really best thought of as a quotient in the derived sense. So it's like, if you like, it's the cone of the map from I to W of R. So it's a derived ring. It's not two derived. It only has two non-zero homotopy groups at most, pi 0 and pi 1. But the pi 1 can exist, and it's extremely useful. And so this is a derived ring, and therefore when I talk about maps like this, I'm implicitly working in derived algebraic geometry. And it's not two derived, as I said, it's only one truncated, but that one truncatedness of these rings corresponds to the fact that at the end of the day, we're getting stacks rather than schemes. Okay, so this is the definition. It's pretty simple. Let me tell you about some structures and properties of this definition to help us understand it better. So it has a bunch of natural structures on it. First is that if you know something about the Witt vectors, you know that the Witt vectors come with a Frobenius. So whenever you have an element of W of R like this, you can produce a new element of W of R, which is called the Frobenius. When R has characteristic P, that's just the same as raising each element to the pth power separately. But when R does not have characteristic P, it's given by a more complicated formula. And it's not too hard to convince yourself that applying Frobenius to a distinguished element is distinguished. And so the consequence is that one gets an endomorphism of X prism. So prob on W induces an endomorphism also called the Frobenius because we're lazy. Phi from X prism to X prism, which is a Frobenius lift, which is in fact a Frobenius lift. So this is a non-tautological statement. What I'm saying is I have this intrinsically defined stack X prism, and then I have some endomorphism of it. And the assertion being made over here is that if you take this endomorphism and you reduce it mod P, you get the Frobenius endomorphism of that stack in characteristic P. So it's a compatibility one has to check. And for experts, what I really am seeing here is that we have a delta structure on the stack. Okay. The second property is, so everything, as I said, was living over spuf ZP prism of R, because you can just forget this piece of data, and you get a point of ZP prism of R. Now, ZP prism of R was this quotient stack, W dist mod W star, and there's a natural substack here you can contemplate, which is you look at those distinguished elements where the zeroth coordinate is actually 0, not just nilpotent. And so that's a very interesting substack. So let me give it a name. So setting D0 equal to 0, it gives a Cartier divisor. And this Cartier divisor is usually called X Hodge state inside X prism. And so these are the two stacks I mentioned at the start of the talk that give everything. And so just restating that earlier discussion in terms of symbols, what I was saying was that yesterday's stack, which was this perfectoidization, was simply the inverse limit along the Frobenius of X prism, and then you do the Hodge state version of it. So you look at this divisor inside of it, given by base change. And so the right-hand side has now a completely intrinsic functor of points description. And so that also gives you a functor of points description of the left-hand side, which yesterday I promised you I would give, but was not able to give because I defined it in some very hacky way as some huge colimit. Okay, so let's do some examples. So let me first try to describe the Hodge state stack of ZP itself. So what does spuf ZP Hodge state look like? And this is actually not that hard. The Hodge state locus was by definition the locus where the first coordinate was 0. So you can write it also as a quotient stack where you first in the numerator look at the locus where the first coordinate is 0, and then you mod out by W cross. But now the condition of being a distinguished element where the first coordinate is 0 is just the condition that the second coordinate is a unit. And so another way to write this is it's the Verschiebung of W cross mod W cross. It turns out for a Witt vector to be invertible, it's enough that the first coordinate is invertible. And then if you know something about the Witt vectors, you can prove that the action of W cross on Verschiebung of W cross is actually transitive. So this quotient stack is point mod something, and it's point mod the stabilizer of any of your favorite element in there. And then if you work out what that means for V of 1, what you get to conclude is that this is the classifying stack of W cross of F. So W cross is the group scheme which sends R to invertible bit vectors. And W cross of F, therefore, is the kernel of Frobenius on that group scheme. So it's invertible bit vectors whose Frobenius is 1. The stack over here turns out to be the classifying stack of this group scheme. And this group scheme is quite understandable. So here's a fact about this group scheme, which I will not prove, but it's not too difficult, is that it has a very concrete description. It's not too big. So W cross of F is actually identified canonically with what's called GM sharp. And what is GM sharp? This is, by definition, the divided power hull of the element 1, so of the identity element of GM. So you take GM, it has some coordinate x, and you formally join divided powers of x minus 1. And the coordinate ring that you get there is the coordinate ring of GM sharp. And that's what this group scheme turns out to be. So it's something you can write down explicitly. It's still non-Noetherian, but as I'll try to indicate later, that the non-Noetherianness of this group scheme should not bother you if you're interested in its representation theory. If you want to understand its representation theory, then the thing that needs to be well behaved is the Cartier dual of the group scheme rather than the group scheme itself. And the Cartier dual of this turns out to be a very nice object, which we'll come back to. Okay, so that's the example of SPOF ZP Hodge-Tate. This divisor inside SPOF ZP prism, and as we just saw, it looks pretty understandable. It's the classifying stack of a group scheme, and this is going to have consequences later for the Rham cohomology. Another example I wanted to mention is what happens in the perfectoid case. So if R is perfectoid, then essentially we already know what should happen. Then the Hodge-Tate stack of R is just isomorphic to R itself. And therefore, the perfectoidization of R also ends up being isomorphic to R. So nothing new happens for perfectoids. But in general, something does happen. And maybe one point I should have made is that at the very start is that, so yesterday when I said X_perf was the best approximation of X via perfectoids, from a similar perspective, X prism is the best approximation of X by prisms. And prisms were somehow invented to be deperfections of the notion of a perfectoid ring. And so it's therefore quite unbelievable that if you perfect the prismatization, then you should just get the perfectoid theory. But if you do the non-perfect theory, as we're doing now, you'll get a little more information. And I'll try to give you some examples of exactly what information you get. Okay. And I wanted to mention one more example, which is, let's take the stack A1 over spec FP. So the affine line in characteristic P, and let's look at its prismatization. So what does this look like? If you go back to the definition up here, you're supposed to give this piece of data and this piece of data. First is a Cartier-Witt divisor, and the second is this map. But if you live in characteristic P, then it turns out that the Cartier-Witt divisor can be canonically identified with P. So this map is redundant. And instead, what you need to give is just a map from W of R mod P into your target X. And so for A1, what that means is that this stack is actually just the quotient stack W mod P. So it's a pretty explicit quotient stack. And it has some other structures. So one thing I should say is that the construction that takes X to X prism, just by virtue of its definition, it takes products to products. Because the piece of data you had to give was like a Cartier-Witt divisor and a map from something into X. And so if I give you X and Y, then the data will just come along for the ride. And what this means is that if you input something which has a ring structure, then the output also has a ring structure. And so A1 has a ring structure. And so therefore, the A1 prismatized also has a ring structure. And that's obvious now from this formula, because the right-hand side is indeed a ring of some sort. So this is as ring stacks. And to make the story more concrete, let's specialize even more. So on FP algebras R, so the test objects for the prismatization were all p-nilpotent rings. But if you restrict attention to just the FP case, which means you're looking at the Hodge state locus. You can convince yourself that W mod P is a very explicit stack. So I want to give a description of a stack, and the way I'm going to do it is I'm going to describe first what the coarse moduli space is, and then I'm going to describe what the stabilizers are. And it turns out that the stack is actually a gerb over the coarse moduli space. So I'm just going to tell you what the coarse moduli space is and what the generic stabilizer is. And so the concrete statement that you get is that pi 0 of W mod P, and pi 0 here means the coarse moduli space. I'm thinking of it as a functor valued in rings, and so calling it pi 0, but it's the universal sheaf of sets that W mod P maps to. Pi 0 of W mod P is just GA. If you think about what Witt vectors are, multiplication by P is locally at least surjective onto all the Witt vectors and except the first one, and it doesn't hit the first one at all. So what's left over is just that first coordinate, which is a GA. And the stabilizer, which is the pi 1, is the kernel of this map, multiplication by P. And again, a similar calculation to what we did above for over here. If you try to carry it out now, what you will see is that pi 1 of W mod P is GA sharp, which is defined similarly. So this is the PD hull of 1 in GA, of 0 in GA. And these are not just as stacks, but as ring stacks or other modules. So pi 0 of a ring stack is a sheaf of rings. And in this case, the sheaf of rings is just GA, the functions. And pi 1 of the ring stack is going to be a module over the sheaf of rings. And it's just the obvious way in which GA acts on GA sharp. If you know a little bit about how derived rings work, you know that any one truncated derived ring is a square 0 extension of its pi 0 by its pi 1. And so this stack, W mod P over here, is a square 0 extension of GA by GA sharp, but placed in homological degree 1. And this is going to be extremely useful in a few minutes. Okay. So those are some examples I wanted to mention for now. I'll do one more example in detail when I talk about the Rham cohomology. I just wanted to make one remark, which is if you've heard about prismatic cohomology, then the coherent cohomology of these stacks is prismatic cohomology of X in good cases. I mean, this is why they were invented, so it's not surprising. And many cases cover everything you might run into in practice. Maybe if you're doing some infinite dimensional stuff, you have to be a bit more careful. Okay, so those were some general comments about what the prismatization is. I gave you the definition and some examples. What I want to do next is I want to talk about some applications of this and the process tell you a little more about what these stacks are. And I'm going to first talk about applications to de Rham cohomology, and then applications to Galois representations. Okay, so let's turn to de Rham cohomology. So let me explain some statements about the de Rham cohomology of characteristic P varieties that one can prove using this stacky perspective. And so here's kind of a basic theorem about what these stacks look like in the characteristic P case. So let's say X over FP is a smooth variety. I have this Hodge state stack of X, which, if you think about its definition, it has a natural map to X. If you're thinking in terms of this ring stack, W mod P is just the map from W mod P to GA given by this calculation. And so I want to make some statements about this map. And so the first statement is that this map is actually a torsor. So pi is a torsor for a group stack. And the group stack is the classifying stack of the tangent bundle sharp. Sharp, again, means you do the PD hull of the 0 section. These sharp constructions show up very naturally when you work with the Witt vectors. The second statement is its cohomology is de Rham cohomology. So more precisely, if you did R pi lower star of the structure sheaf, you just get the de Rham complex of X with the de Rham differential, thought of as a complex over X by the magic of characteristic P. So the de Rham differential is not linear over functions, but it is linear over Pth powers of functions. And so maybe I should put a F lower star somewhere to make this more believable. And that gives you a quasi-coherent sheaf on X whose global sections are the de Rham cohomology of X, which is this side. And the claim is that that object is actually just a push forward of the structure sheaf from the Hodge state stack. And so when you take global sections of this isomorphism over here, what it will tell you is that the coherent cohomology of the Hodge state stack is the de Rham cohomology of X, which is very similar to what I said yesterday in characteristic 0 for the Simpson stack. And then finally, I also want to tell you what quasi-coherent sheaves look like, at least what perfect complexes look like. And so you can ask, is there a good description of perfect complexes on X Hodge state? And the previous answer suggests that, well, maybe they should, like if the unit object over here corresponds to the de Rham complex, then maybe this should have something to do with D modules. And it does. The precise connection I'll make in tomorrow's talk. But right now, let me just give a description. So what it looks like is dB co with finite support on the completed cotangent bundle of X. And then there's a twist. All right, so let me say what's going on over here. So this is a GM gerb. And so I'm talking about sheaves twisted by a GM gerb, twisted sheaves, as you might have encountered before in the study of Brar groups. And this condition of finite means that the support is finite over X. And so roughly modulo some decorations, sheaves on X Hodge state look like they have to do with the cotangent bundle. And sheaves on the cotangent bundle, if you went to Moloch stocks or maybe Shen stocks in the first week, you would know that they are essentially Higgs bundles. And so this is giving you some relationship between quasi-coherent sheaves on X Hodge state and something having to do with either Higgs bundles or D modules or something of that flavor. And tomorrow I'll sort of make more precise statements about this this equivalence. But for now, I think let me just leave it here. It's a pretty natural looking object from algebro-geometric point of view.
That's a question.
Oh, as a zoom. Okay. Yeah, sure.
Is this P curvature coming in here?
Is the P curvature coming in here? Yes.
Okay.
Okay, so since Arthur is asking this question, I have to say, so what's going on over here is D modules have a notion of P curvature, and that allows you to localize them over the cotangent bundle. And so this category is just going to be the category of D modules with some nilpotence of P curvature assumption. Thank you. I don't know if it makes sense to pause for other questions from the room, but if so, someone there should decide this, otherwise I'll keep going. Going once, going twice.
Yes. Does Bhargav hear me too?
I can kind of hear something.
Does it help if I speak louder?
It does help.
My question is, this thing is called X Hodge state, but in the end, the cohomology you get is de Rham cohomology. So could you comment on why you wouldn't call it X de Rham?
Yeah, so that's a good question. It turns out in characteristic P, Hodge state cohomology and de Rham cohomology are canonically identified. But there's a mixed characteristic version of this statement. So what I should have really formulated is a statement over any perfectoid ring. And then a lot of these statements will still be true, except what shows up in number 2 would not be the de Rham complex, but something called the Hodge state complex. So the short answer is that in characteristic P, Hodge state and de Rham are off by a Frobenius twist, which is why what I get over here is the Frobenius push forward of the de Rham complex rather than the de Rham complex. Yeah, thanks for the question. Okay, so I'll keep going. So I wanted to give just some very brief sketch of the proof, just to give you a sense of what goes into this. It won't be, it's not the kind of proof you would give in a class, okay? But let me just give the idea. So what is the functor of points of X Hodge state? If you unravel the definitions, what you're supposed to do is you're supposed to take X and then evaluate it on W of R mod P rather than on R. And earlier, I was telling you that W of R mod P looks like it's a square zero extension of R by something having to do with R sharp. And so one essentially just follows from that by deformation theory. So use deformation theory. Deformation theory tells you that if you try to evaluate X on a square zero extension, what you need to know is first how X evaluates on the thing that's being thickened, and then you need to know something about derivations from the cotangent bundle of X into the ideal of the thickening, and that's where this BTX sharp term comes from. The map down to X is the value on the unthickened object, and then the fibers have to do with the deformations. And then for 2 and 3, I'm not going to give you a proof in the case of the torsor of interest, but let me tell you what's going on for the trivial torsor. So for the trivial torsor, rather than the interesting torsor that we have, this is a very general story. You can ask, how do you understand the push forward of the structure sheet from BG down to a point for a group scheme G? And under some reasonable assumptions in the group scheme, the answer to this is controlled by the Cartier dual. And so what you need over here is the calculation of the Cartier dual of this group scheme. So let me first say what I mean by the trivial torsor. So the trivial torsor is just the projection map from this classifying stack down to X. What you need to do is you need to use that if you take BTX sharp and you look at its Cartier dual, what you get is exactly this completed cotangent bundle. And in this process of passing to the Cartier dual, what usually happens is that quasi-coherent sheaf on the classifying stack of the thing you're taking a dual off end up being related to quasi-coherent sheaves on the Cartier dual. And so this is this point I was making earlier, that even though the group scheme that appears over here looks kind of bad or non-Noetherian, what's really relevant is what its Cartier dual looks like. And the Cartier dual looks very nice. It's the formal completion of a smooth variety along the smooth subvariety. And that's where the theory has a lot of finiteness to it. So that's kind of a very rough sketch of what goes into proving these statements. It's not too hard to turn this into complete proofs. But for now, I just want to just keep in mind the statements. You can forget about the proofs if you're not interested. But the statements are that this is a torsor and that its cohomology or sheaf theory has to do with either the de Rham complex or some twisted version of Higgs bundles. OK, so let me give you an application of this. So here's a corollary of this. This was observed by Petrov, who, in fact, did something really fun with it. So what he proves is that, let's say, X over Fp is F split. So it's Frobenius split, meaning that OX to F lower star OX splits. Then the theorem is that the de Rham complex is actually formal. So if you do this Frobenius push forward of the de Rham complex, it's actually isomorphic to the direct sum of its cohomology sheaves. Shifted by minus I, and these cohomology sheaves actually have a name. They're just given by differential forms again via the Cartier isomorphism. And so this is just a very classical statement. One could have asked this question as soon as one knew what F-split varieties were. There are tons of examples of these, like flag varieties. But I believe this statement was not known, or maybe not even conjectured, until it was proven. And he then uses this to conclude that the Hodge to de Rham spectral sequence degenerates for some interesting classes of varieties, including B of a reductive group G. And so again, this was known in special cases for special groups via arguments specific to those groups, or in low degrees, but not in this generality. And so what's the proof It's actually completely simple given what I've already told you above. So the left-hand side is what you get from the Hodge stack by the previous theorem. The right-hand side, by the proof sketch of the previous theorem, is what you would get from the trivial torsor. And so this is essentially trying to say that some torsor is split. If the torsor was split, you would have this isomorphism. Now, the torsor is not split, but that also doesn't use the F-splitness hypothesis yet. And so what you observe is that for any x, this torsor pi x Hodge state to x splits after Frobenius pullback to x. So pull back along the Frobenius on x splits the torsor, and this is just because of how it was defined. It came from some deformation theory. And if you know something about how square zero extensions work, then you know that Frobenius tends to kill square zero ideals. And so this is generally this is always true, and therefore, if x is F split, then you get the conclusion you want by cohomology and base change. Like you're trying to show this object is split. What the first line tells you is that its Frobenius pullback is split, but then the assumption tells you that if something splits after Frobenius pullback, it must be split to start with. Yeah, so it's a nice statement about de Rham cohomology. It has some very concrete examples, and I believe my impression is that we do not yet have a non-stacky proof of this. Maybe if Petrov is there, he can confirm or deny this. Okay, so that was one application I wanted to talk about. I was going to tell you about a theorem of Drinfeld, which was a refinement of the Deligny-Lousy theorem, but maybe I'll save that for the end if there is time. I want to talk about something about Galois representations before it's too late. So, yeah. So p-adic Hodge theory, if you look at its history, it was not invented to study de Rham cohomology of characteristic P varieties. I don't think this is the kind of question that one was interested in studying when one, I really mean Fontaine, was defining these big rings. He was really interested in understanding properties of Galois representations. And so do we learn anything new about Galois representations from this stacky stuff that I've been telling you about? And it turns out we do. So I wanted to give you one example of that. And so this will require some definitions. So let me first define what an F crystal is. So X is, again, a p-adic formal scheme. It's soon going to be something like spec ZP, or spuf ZP. An F crystal on X, and maybe there should be an adjective that says prismatic F crystal, but we'll just drop it. An F crystal on X is a pair M comma phi M, where what is M? Well, M is a vector bundle on the stack, X prism. So it's a prismatic crystal, if you like. And then phi M is an isomorphism between M and its Frobenius pullback, but only after you remove the Hodge state ideal. So it's an isomorphism of phi upper star of M, invert the Hodge state ideal, with M, invert the Hodge state ideal. And of course, in this definition, it wasn't really important I put vector bundles here. I could have also talked about F crystals in like perfect complexes or some other kind of structures. Anyways, this is what I want to talk about, and I got a category over here. So I'm going to call this category the category of prismatic F crystals. And the notation is going to be the following: vect phi X prism. Okay, so this is kind of the natural category, or this is the first guess, at least, a first attempt at defining a natural category of coefficients for prismatic cohomology. And so what do I mean by that? Let me give you an example. So in Hodge theory, once you define the notion of a variation of Hodge structures, it's kind of really important that you have some examples, and then we know that the cohomology of a family of smooth and proper varieties gives you an example of a variation of Hodge structure, so the definition and the theory is rich enough. Analogously over here, if f from x to y is smooth and proper, then you can form the push forward of the structure sheaf of X prism, and this is naturally a prismatic crystal in perfect complexes, at least. Then there are some questions about, well, are the cohomology sheaves vector bundles or not? And those tend to have to do with more subtle behavior of the topology of the fibers, like whether or not there's torsion in their cohomology. But at the level of complexes, this is an example. So the analog of variations of the Gauss-Manin connection is in the picture. And then if you've, maybe I'll just say this verbally, if you've encountered the notion of F crystals over a perfect ring of characteristic P, then it would literally be the same definition. So it's the usual notion of F crystals in cases where one had such a definition. And so I'm trying to make the point that this is a reasonable category of coefficients for prismatic cohomology. Now I've told you a little bit about what this prismatization functor looks like on characteristic P inputs. What would it look like in mixed characteristic, in sort of genuinely mixed characteristic situations? Well, one way to answer this question is to try to describe this category in some mixed characteristic situations. And so here's a theorem about what this category looks like in that case. So theorem. This was joint work with Schultz near the start of the pandemic. Sorry, I didn't look up the dates. So let's say X is just buff of OK, where K is a finite extension of QP. Then what is this category? This category of prismatic F crystals on SPUF OK is nothing but the category of crystalline Galois representations. So ZP representations of the absolute Galois group of the fraction field K, which are crystalline. So crystallinity was a notion invented by Fontaine using these big rings, and it was trying to capture the structure that the cohomology of a variety over capital K should have if the variety had good reduction. And if the variety had good reduction, then that variety would extend to a smooth and proper scheme over OK. And so you would expect that we would have an object on this side, and the theorem essentially saying that those objects match up. And more, but that's the easiest thing to say. And so we get a new perspective on what these crystalline Galois representations are. If you haven't seen them, then I'm not sure I can give you definitions right now, but just take this as a definition. Although maybe that's okay. Well, anyways. I want to tell you something we can do with this equivalence. So let me make a first remark about this. So this is what happens in the case of the point, so to speak. I'm talking about just DVRs. And you can ask if there's a higher dimensional version of this, and it exists. So there's a higher dimensional version, was worked out very nicely by, okay, there's too many names, so I'll just use abbreviations. So Guo and Reinecke, and then separately Du, Liu, Moon, and Shimizu. So there's a notion of crystalline local systems devised by faultings, and then they prove a similar statement with a slight modification of the left-hand side. Okay, so that's the theorem. The claim is that this theorem actually lets you do something interesting or prove something interesting about crystalline Galois representations by understanding the geometry of these stacks. And so I want to explain some recent joint work with Toby G. And Mark Kissin on a concrete statement about Galois representations. One can prove this way. Toby and Mark are both there, I think. And the statement was motivated by the weight part of Serre's conjecture. But if you want to understand the motivation better, I am definitely not the right person to ask. You should ask my co-authors. The statement, on the other hand, that I'm about to explain is purely geometric, and so I can actually go through with that. Okay, so let me do a construction. So what I'm about to do is I'm going to tell you that associated to a crystalline Galois representation, you can write down two invariants, two numerical invariants. well, associated to any Galois representation, you can essentially write down these two numerical invariants. One has to do with the characteristic zero representation. One has to do with the mod p representation. And there should be some relationship between them. And there's an obvious relationship between them. And then what the stacky perspective lets us prove is there's actually a better relationship between them. And let me try to now formulate this more precisely. So let's say K is the residue field of my discrete valuation ring OK. So this part of the talk, the rest of the talk is going to be a bit more detailed than my previous talks yesterday and the first half of this talk. So K is the residue field OK mod M. OK, maybe not first half, first 3/4. A is going to be what's called the Breuil-Kissen prism. So you take the bit vectors of K and you adjoin a formal power series variable U. And if you choose a uniformizer in K, you can write OK, the ring of integers, as A mod an Eisenstein polynomial. This is a uniformizer. And we're going to regard this ring A as having a lift of Frobenius phi determined by sending U to the P. Prisms are, A is going to be an example of a prism, and a prism comes with such a lift. And so the first claim is that you get a natural map to the stack SPUF OK prism out of this. I'll call this map rho. It's a map from SPUF A to the stack where prismatic crystals live, SPUF OK prism. So it's a way to probe the geometry of the stack. And if you remember, to give points of the stack, I basically have to specify Cartier-Witt divisors and then some additional maps. And so to specify a Cartier-Witt divisor, I need to specify a distinguished element. So I need to tell you a distinguished element in the Witt vectors of A. And this is determined by the Eisenstein polynomial. So this is associated to E applied to the Teichmuller review, thought of as an element of W of A. So if you unwind the definitions of what it means to give a map of stacks like this, you'll see that this distinguished element, this element is distinguished, and that it lets me build this map. And a basic fact is that this map is faithfully flat. So it's a cover of the stack. And so if you're trying to understand sheaves here, you can try to understand them in terms of sheaves here together with some descent data. And and the same for crystals. And so crystals over here are the same as crystalline Galois representations, as I said before by the theorem. And so what this lets you do is it allows you to attach modules over A to crystalline Galois representations. What you get is you get a functor from this category of crystalline ZP Galois representations of K into some category of vector bundles with the Frobenius over this ring A. So it's a much more linear algebraic object compared to what a crystalline Galois representation is. And this is the kind of maneuver one is always doing in p-adic Hodge theory, where you try to translate questions about Galois representations into more concrete linear algebra questions. And so let me give this functor a name. So T goes to M of T. Sorry, was there a question?
No question.
No question. Okay. Right. So, so this invariant actually, I mean, this is one way to describe what these modules are, but actually this was this construction existed before this prismatic business. So this is called the Breuil-Kissen module. So this is the category of Breuil-Kissen modules, and Mark explained how to construct M of T given T. I just presented one way to think about it in terms of this picture I'm trying to explain. And what I want to do is I want to explain that there are two numerical invariants associated to M of T. And those two numerical invariants have some extra, some unexpected relationship if it comes from a crystalline Galois representation. So let me first recall a procedure for extracting numerical invariance out of isogenies. So let me say xg is going to be my notation for a certain space that people might have studied before. So G is GLN. I'm talking about vector bundles. And the space I'm talking about is the affine Grassmannian, but mod is natural group action. So if you don't know what this is, that's totally fine. I will give you the functional points description in a second. So xg of R, it turns out to be pairs of vector bundles M and N over R power series U, together with an isogeny between them, a U isogeny between them, or equivalently an isomorphism after inverting U. So sorry, it's this plus an isomorphism, M1 over U with N1 over U. So if you're looking at field valued points, you're talking about two finitely generated free modules over a DVR together with an isomorphism of their rationalization. And you can classify what those look like over a field. And so here's a fact, which is just the classification of modules over p-adic. It says that over k equals k bar, if you sort of look at the fibers of xg over an algebraic closed field, then the topological space xg has a nice description. It's actually just n tuples of integers, z to the n, ordered, well, n tuples of ordered integers. So this is a1 bigger than a2 bigger than ... bigger than an, sitting inside z to the n. So there's the representation theoretic way of saying this is these are the dominant co-characters. But it's just this tuple of integers in this concrete case. And then the closure relation over here on xg corresponds to a standard ordering on n tuples of integers like this. And I don't want to write down what this ordering is. I'm hoping people have seen it before, but roughly 2, 0 lies above 1, 1, because you can sort of, if you have two things stacked together, you can move it down and you get two things adjacent to each other. Or if you're thinking in terms of modules, a cyclic module of length 2 over a DVR can be degenerated into a product of two cyclic modules of length 1. And that's the kind of closure relations that are being captured over here. And so why am I introducing this object? I was trying to tell you something about these Breuil-Kissen modules, and now I just told you a procedure to take, I told you some linear algebra business stuff, and so here's why I did it. And so this, back to our setup, this Breuil-Kissen module M of t, it gives you a point.
For this fact, I'm just wondering why you have to assume k is a bar.
Sorry, I didn't hear the question.
I'm wondering why, for the fact, you have to assume k equals k bar.
Oh, maybe you don't for GLN. I was just worried about torsors for the group you're quotienting by causing problems. It's probably okay for in the GLN case in general, yeah.
Okay.
Thanks. I should have said everything I'm saying right now also works for all reductive groups. I was just doing it for GLN. So this M of t, it's an object over here. And so it's a module, it's a vector bundle over A together with an isomorphism between the Frobenius pullback of that bundle and itself after inverting this divisor, corresponding to the Hodge state ideal. And so if you like, it gives you a point, lambda, which is a z point, or which is a zp, or w of k point, sorry. W of k point of this affine Grassmannian quotient. Because take this to be your Breuil-Kissen module, and then take this to be its Frobenius pullback, and then take this to be the isomorphism you have between them. You have to do a change of variables, u to u minus p, but you get a data like this, and what you can therefore do is then you can restrict to each geometric fiber. And so you get lambda of t qp, lambda of t fp. These are points in the fibers, and therefore they're just n tuples of integers, ordered integers. And just by virtue of this construction, the characteristic p point is the specialization of the characteristic 0 point. And so because of how the closure relations work over here, what you get is a relationship between them. So you get that if Okay, there's a chance I'm off by a sign, but I think you get that the characteristic 0 point is more general than the characteristic p point. And okay, so this was something I just did in terms of linear algebra. Now, if you go back to where t came from, or m of t came from t, which was a crystalline Galois representation. It turns out that the QP invariant and the FP invariant can be thought about in terms of this crystalline Galois representation. In fact, the QP invariant is literally just the sequence of Hodge state weights of that Galois representation. And the FP invariant, up to some ambiguity, is determined by the restriction of by taking this integral representation and reducing it mod p, and then doing something combinatorial with it. And so, roughly speaking, this is an invariant of the characteristic 0 representation, and this is an invariant of the characteristic p representation, and they have this relationship. From the Galois theoretic point of view, the fact that they have this relationship is already non-obvious. I think it's related to some conjectures of Serre that were proven by Caruso maybe 20 years ago. And our theorem is that something better happens in the unramified case. So let me say the theorem. So assume K is unramified. Then there's actually a sort of stronger ordering on the same set, and they're related in the stronger ordering. So the QP invariant is what's called up arrow from the FP invariant. And so this up arrow relationship, it has a combinatorial definition. Essentially, I mean, I'm not going to be able to reproduce it here. I'll give you a geometric definition in a second, but roughly the order relation over here is determined by these kinds of moves I was talking about, where you take sort of a few things stacked together and move it to the right. And for the up arrow relationship, you do something similar, except things have to be multiplied by p. And so we're saying that the relationship between these two is of that stronger sort. And to give you an idea of why, or what this up arrow is, and also to tell you why this stacky perspective is relevant to this, let me just tell you the proof in 2 lines.
Yeah, just to let you know, we're running short on time.
Yeah, I'll try to finish. I have only half a page left in my notes. Sorry, yeah. So I'm going to let YG be the mu p fixed points of the space xg that I discussed before for the scaling action. Of mu p on the variable u. So xg was parameterizing lattices over R power series u, and then u has a mu p action, and so you can look at that induces a mu p action on this space, and then you look at the fixed points. And so the fact, which is we sort of used a lot of work by Riesch and Williamson to prove, is that the topological space underlying YG is the same, has the same underlying set as before, but the up arrow relationship. Sorry, is there a question?
No, I think it. No.
Okay, let me just finish. Sorry, and then I'm happy to answer questions. And so this is the geometric realization of this up arrow relationship. The usual closure relation came from just thinking about the space xg, and this up arrow relationship comes from thinking about its mu p fixed points. That's kind of the punchline. And so what you need to do is, to prove this relationship, you need to explain why this point lambda t that you have actually refines to a point of the mu p fixed point locus. That's not literally what happens, but at least you need to produce a mu p fixed point somewhere. And so here's how you get the mu p fixed point. And now I'll stop after I draw this diagram. So here's SPUF A. You look at this map you had to SPUF OK prism given by u. So in the unramified case, the Eisenstein polynomial is just u plus or minus p. And I'm going to tweak it. So I'm going to replace p with this element v of 1. So it's a perturbation of the Eisenstein polynomial. But the advantage is that this map over here is actually mu p equivariant. So it factors this way. And then you take your prismatic F crystal over here and you pull it back over here and you get a mu p equivariant F crystal somewhere, and then you can use that to prove the relationship. So I'm sorry, I didn't give details. I'm out of time. All I want to say is formulating things in terms of the stack was useful because it allows you to map objects like buffet mod mu p into it. And if you were just working in terms of sites, this would be a little awkward, at least, to formulate. I'll stop. Thank you.
Are there questions? Okay, I think there are no questions today. So thank you again, Bhargav, and we'll see you tomorrow.
Yep, thank you.